So, welcome back. This lecture, this class, we augment the surface tension, which we had an outing, last outing, where we discussed the effects of surface tension, and today I propose to take you to capillarity and to explain capillarity. We talk about the angle of contact which two interfaces have, the ideas of drops and bubbles and cavities, so in doing that, the surface of a liquid near the plane of contact, here with another medium is more often than not, normally, usually, or in general, is curved. Okay. That curve could be a straight line also. That curve could be a plane also. That curve could be concave, and that could be convex. Okay. So these are the situations. Now, angle of contact theta is defined as an angle between the tangent to the liquid surface at the point of contact and the solid surface inside the liquid. Now, these are the two situations that we have here. One in which there is a formation of a droplet. Theta is shown to be obtuse, more than 90 degrees, and this is the case of water drops on lotus and other leaves. In many a situation, what is called, we can see it in the morning on the grass also, and that is known as has a beautiful name, Shabnam. Okay? The droppings of the night. Shabnam. Shab means night and Nam means it is Nam means that you understand. Okay? Now this theta determines, here the theta is acute and the drop is spreads. Normally it happens when you take a clean plastic or clean glass. In many situations, if you have the liquid is kerosene, then it spreads. Water having a different surface tension than the other liquids which make formations like this, it forms droplets. So theta determines whether the liquid forms droplets or spreads. Now, I am deviating from what I took before. I used S for surface tension. But there is times there is a confusion, so I am taking rather T as the symbol of surface tension with expressed in newtons per meter. Okay. So I have just shown here, I enlist TLA, the liquid air interface, TSA, solid air interface, TSL, solid liquid interface, etc. Now if we look at the figure B here, okay, and I show that this angle is an acute angle, theta, TSA on this side like here, TSL on this side like here, and TLA is making between the liquid and air, the angle is acute. So I can write TLA cos of theta, TLA cos of theta, the result part in the horizontal direction, plus TSL in the same direction must be balanced by, in the equilibrium condition, by TSA, okay, the solid air interface. So this is balancing the cos theta component on this side and this side, okay. Well, if TSL is greater than TLA, like it has been shown in the figure A, that this has to be greater than that because this plus this cos of theta, okay, they together, they are balanced by this figure A. Actually what happens is that the molecules of the liquid are attracted strongly to themselves. Liquid molecule is strongly attracted by a liquid molecule. Such forces are called cohesive forces, okay. If in a matter the molecules of the same variety of the same substance, they attract each other, such forces are called cohesive forces. And of course, the molecules of the liquid are attracted weakly to the solid molecules, weakly, okay. So this is what are the adhesive forces. Now in doing so, in creating the liquid solid interface here, in case the liquid does not wet the solid, the liquid does not wet the solid, it costs a lot of energy to create this liquid solid interface, okay. We'll discuss otherwise for this thing. So let us take the second condition, corresponds to the figure B over here, where the theta is acute. Theta is acute, okay. We have TSA as the surface tension between solid and air, between solid and liquid, and between liquid and air. So T represents the amount of surface tension in newtons per meter, as I told you before. So in this second case, in figure B, the theta is acute, okay. Then what happens is that the molecules of liquid are strongly attracted to solid molecules, which is contrary to the first case, where it was not so. The molecules of the liquid are strongly attracted to the solid molecules. So what happens? In that case, the value of T between the solid and liquid interface, that reduces. Cos theta increases. The value of cos theta increases, and it does so. The cos of theta is maximum, theta is equal to 0, and minimum, that is when theta is equal to 90 degrees. So when the cos of theta increases, the theta decreases. Of course, theta is acute. And the examples are water and clean glass or plastics, kerosene oil, which is called mitti ka tel or ghastrate on any surface, and water blended with soaps and detergents, etc. So you go on next to talk about drops and bubbles. So let's talk about drops, cavities, and bubbles. Normally drops and bubbles. Now we know that free liquid drops are droplets and bubbles are spherical in shape. So are soap bubbles, and soap bubbles are stable. And after this discussion, I would suggest that you answer why the soap bubbles are stable. Okay, try to find it out all by yourself. Now, any interface between a liquid and a gas, a liquid air interface in this case, has energy. And the minimum energy for a given volume requires least surface area, which is obtained in the shape of a sphere. The area 4 pi r square of this is the minimum area for a given volume, which will be in this case 4 by 3 pi r cube. It is similar to the case of the area of a circle. The shape for the area given area to have a shape, the best possible shape is a circular shape. Okay, so this is something which is passed on to you from me. Also, I have given a schematic diagram of a drop of liquid, spherical in shape. So there is an interface which is the liquid air interface. Okay. There are two pressures which have been shown, pressure inside and pressure outside. And pressure inside has to be larger than pressure outside, which has been shown here. Now, for the stability of the drop. Now, if we try to increase the radius from r to a larger value of r plus delta r to r plus delta r, then an extra surface energy is calculated, and that is 4 pi r plus delta r whole square minus 4 pi r square into TLA, where this is the surface tension with liquid air interface. I take out 4 pi and expand it r square plus 2r delta r plus delta r square minus r square, so r square and r square cancel, and this delta r whole square, this is negligibly small, so we ignore that. And what we obtain is that the extra surface energy is 8 pi r delta r into TLA. Okay. This loss of energy is equal to the gain due to expansion. Why? Delta P is equal to Pi minus P0, so expansion takes place, and therefore we write the work done W is equal to the pressure difference into 4 pi r square into delta r. Okay. When we equate the two of them, this equation and this equation, we write it Pi minus Po 4 pi r square delta r is equal to 8 pi r delta r TLA. So pi and pi cancel, one r cancels with another r, delta r cancels with delta r, and one r cancels with this r, and 4 and 8 we divide, you get 2, and the final result that we obtain is Pi minus Po is equal to 2 TLA upon R. So, in general, for a liquid gas interface, convex side has greater pressure than the concave side. Now, I have shown a cavity inside a liquid where this is air and the outside thing is it has got only one interface, and therefore we can write for this cavity also, like in previous case of the drop, that Pi minus Po is equal to 2T upon R. Of course, T is for the liquid air interface. But when we have a bubble normally a soap bubble, so inside there is air and outside also there is air. There is a thin film of liquid which has got now two interfaces. One liquid air interface inside and the other outside. It has been shown exaggerated, but normally this is very, very thin. Okay, because it has got two interfaces, therefore the formula which we got, Ti minus Po is equal to 2TLA upon R, that turns out to be equal to Pi minus Po is equal to 2TLA upon R plus 2TLA upon R for the two interfaces, and that makes it 4TLA upon R. Okay. So that does for the drops, cavities and bubbles. So we deal in the last of the topics, that is capillary rise. Capillary is a hair thin bore in glass or any other material. It's found naturally. For example, in the fibers of the trees, capillaries are formed. So, in spite of gravity, water rises in the capillary. Gravity is down, the water rises like this. And the surface of water in the capillary, as has been shown over here, is concave. Conversely, if we had, I'll explain to you, if I had instead of this mercury was there, which does not wet the glass sides, then what will happen is that instead of being a concave spherical surface, it will be a convex spherical surface, and there will not be any rise. Instead, there will be a fall from the level which has been shown. So this is a very simple experiment which has been schematically shown to you, and in equilibrium condition we find that the liquid rises in this capillary, which has a radius of A meters or whatever units we are taking. Okay, rho is the density of water or liquid under consideration, and H is the capillary rise. Now this thing has been shown, elaborated over here. Actually, this is A, and this is the center of the spherical surface which is built by this concave surface of the liquid. So what we find is that there is a pressure difference between the two sides of the top surface. Okay, and that can be shown as the internal pressure minus Pa is equal to 2T upon R, as has been derived earlier. Now R is cos theta is equal to A, and therefore R becomes equal to A upon cos theta. So I substitute that value 2t A upon cos theta, and so that I get the pressure difference, okay, to be 2t cos theta upon A, which has been given over here. Okay. So see, you can check that T is in newtons per meter, and this A is in meters, so this becomes equal to Newton per meter square, which is the dimension of the unit of the pressure, which is newtons per meter square. So we check that. Okay. Thus the pressure of water inside the tube, just at the meniscus, this interface which has been shown over here, is less than the atmospheric pressure. Okay. Now let us consider points A and B, which I will try to show you at the same level in the liquid. Points A and B. So therefore the pressure at A must be equal to the pressure at B. Okay, and the pressure therefore we write the pressure at B as equal to P0 plus rho GH, which is equal to PI or PA. Okay, so rho GH becomes equal to PI minus PG, which is 2T cos theta upon A, which gives us naturally H is equal to 2T upon A rho G cos of theta. 2T upon A rho G cos theta. Now T for a given set of materials, that is the liquid and glass and the air combination that has been there, the surface tension, T is a constant, rho is a constant, and G is a constant. So I can of course vary A, and so H also varies. So we find that H into A is equal to 2T upon rho G cos of theta. So everything else being the same, H into A is a constant, which means if I draw an XY curve like this, where H versus A or A versus H, we get a graph which is the representative graph of Y is proportional to 1 upon X. Yani Yx is equal to a constant. Of course, this asymptotically goes to infinity, and this also goes to 0 value. Okay. So if A is low, then H is high, and if A is more, then H of course is very small. So this is about the phenomenon of capillarity, which takes into account the concerns of drops and bubbles, which needs angle of contact between the surfaces, which we have discussed here, and of course who is responsible for this capillary rise or capillary fall in the case of mercury, for example. It is nothing but surface tension. It was an application of surface tension, and of course one of the topics which is discussed normally is the role of soap or detergents. Okay, it's not in my scope because it requires many testing things to make here on the board. I am not able to show you how the detergent molecules, they help take out grease, etc., and similarly soap take out the impurities from the clothes that are being washed or the parts of your body that are to be cleaned. That cleaning and washing, that is what I expect you to look into, whatever book you have, okay, because it's not possible for me with the limited resources that I have to deal in that thing. So friends, here the almost the topic of the mechanical properties of liquids comes to an end, and we are now on to the thermal properties of materials, okay, and thereafter we'll talk about thermodynamics. So once again, I like to end my lectures with this. So and I have received a few questions of late. I want your questions to be addressed to me so that I can address the answers and share with my views. Thank you very much. See you shortly.